Hi everyone, in this video we'll solve problem 9.93 from the book Thermodynamics in Engineering Approach, Cengel 9th edition. Here the statement of the problem 9.93. An aircraft engine operates on a simple idle Brayton cycle with a pressure ratio of 10. Heat is added to the cycle at a rate of 500 kilowatt. Air passes through the engine at a rate of 1 kg per second, and the air at the beginning of the compression is at 70 kilopascal and 0 centigrade. Determine the power produced by the engine and its thermal efficiency. Use constant specific heats at a room temperature. Remember, in an aircraft engine, open gas turbine cycle is worked. This is a simple open gas turbine cycle. 1 to 2 is isentropic compressions that occur in the compressor. Then 2 to 3 is constant pressure heat addition process is occur in the combustion chamber by injecting the fuels, due to which combustion is occur. Then this high temperature high pressure fluid is expanded in the turbine and it give you the net power output that is connected to this common shaft, and finally and leaves at a state point 4. This is a common shaft, that is some of the work that is produced by this turbine is also utilized for this compressor, so it can easily compress the incoming air from pressure P1 to P2. Now let me draw the TH diagram of this open gas turbine cycle. First is isentropic compression 1 to 2, then combustion chamber at which heat addition at a constant pressure is occur, and then 3 to 4 is isentropic expansion in the turbine. So the 4 to 1 process is missing here because it works on open Brayton cycle. That's why the entropy here is S3 is equal to S4 and S1 is equal to S2. Here the temperature is T1 and here the maximum cycle temperature you will observe, that is at T3. Also let me draw the PV diagram of this open cycle. Open Brayton cycle. Isentropic compression 1 to 2. Pressure increases from P1 to P2. Heat addition is occur at a constant pressure in the combustion chamber. Then isentropic expansion in the turbine, that is 3 to 4, and it is the hot gases and then the hot gases leaves in the atmosphere. So that's why it is open, or heat exchanger is installed here. It recovers the working fluid back to its initial state. P1 is equal to P4 and P2 is equal to P3. Now come toward the statement what data it provided in this Brayton cycle. The first is the pressure ratio, that is equal to P2 divided by P1, also equal to P3 divided by P4, and it is 10. The heat is added 500 kilowatt. So the heat that is added in process 2 to 3 at a constant pressure, that is 500 kilowatt. 1 to 2 required some work input in order to run the compressor, and 3 to 4 will give you the work out when the gases expand to the turbine. The mass flow rate of the gases, mass flow rate of air is 1 kg per second. Pressure P1 70 kilopascal. Temperature T1, that is 0 centigrade, convert into Kelvin. So T1 is 273 Kelvin. We will use the Cp value is 1.005 and the value of isentropic index, that is 1.4. What we need to calculate, that is power produced, W net dot, that is the power produced, and thermal efficiency, that is all requirement. Now come towards solution. Consider the process 1 to 2 as isentropic compressions. You can say that T2 divided by T1 is equal to P2. So we can say that T2 is equal to T1 into P2 divided by P1 is the pressure ratio. That is, now you simply enter the values and you will get the value of T2. You solve this on calculators, you will get the T2 value, that is 527.1 Kelvin. Now the power required to run this compressor, that is W naught N is equal to M dot Cp, change in temperatures T2 minus T1. M dot value is 1, Cp value is 1.005, T2 is 527.1 minus 273. When you solve this on calculators, you will get the power that is required to run the compressor, 255.3 kilowatt. Consider the process 2 to 3 at which heat addition is taken place. From process 2 to 3 at a constant pressure with the help of this combustion chamber that work at a constant pressure. So the heat that is supplied is equal to M dot Cp, change in temperature T3 minus T2. Put the values and find the T3. After solving these equations, we will get the T3 value, and that is 1025 Kelvin. Now consider the process 3 to 4 that is happen in the turbine and is isentropic expansion. You can say that T4 divided by T3 is equal to P4 divided by P3 power gamma minus 1 divided by gamma, and T4 is equal to T3 times into this P4 divided by P3 is the reciprocal of the compression ratio Rp. Now you simply enter the values in these equations and you will get the T4. And you solve this on calculator. T4 value you will get, that is 530.9 Kelvin. Next, you need to find how much power is produced by the turbine when gases are expanded isentropically in the turbine. W dot out, and it will be equal to m dot Cp, change in temperatures, that is T3 minus T4. To solve this on calculators, you will get the power that is produced by the turbine, 496.57 kilowatt. So this is equation 1 and this is equation 2. This is the power input that is required to run the compressor. This is the power output that is produced by the turbine. So the net power produced will be its difference. So the net power produced is 241.3 kilowatt. This was our first requirement in the statement. Set A needs to find the thermal efficiency of the aircraft engine, that is the net power produced divided by the heat supplied to it. The heat supplied is given in the statement, it is 500 kilowatt. After solving this, you will get 0.48, means to say 48% isentropic efficient. And this is our final requirement of this statement. I hope you understand. If still there any confusion, you can ask in the comment section. Please subscribe my channel if you haven't subscribed. Thank you so much.